Continuing from where we left off with the interpretations to probability. In this section, we shall be looking at more of the probability properties, where we shall also be proving them as well. So with this, let's take a look at the first property. Let's just term this to be proposition 1. And remember from our previous sessions, we got to know that probability of A plus its complement should give us what? 1. Now this is the same as the sample space, which we dealt with earlier on. Now with this same thing, we could rearrange them to find the probability of A. Suppose that we know the probability of the A complement. We could also just estimate the A. Now let's look at this proof, which is giving us whatever we have here. So we are just going to prove this formula that we have here. And let's see how it's done. Now remember from the properties of probability, that is the third axiom. Suppose that we let n equals to 2. In this case, we are looking at two events. So we have A1 is equal to A and A2 being equal to 1, the complement of A. Now since by definition of A prime, that is A union A prime is equal to what? The sample space. Remember that the combination of the event as well as its complement is going to give us the entire sample space. So while A and A prime are disjoint, this implies that the probability of the sample space, which is equal to 1, is the same as the probability of the event union of what? Its complement. And remember from the property that probability of A plus that probability of what? A prime. So this is what this is going to yield once we are trying to estimate it. And this, everything that we have in here will be equal to what? 1. So that is how we get to prove this property that we have here. Okay, so that is how we get to do that. Now this property that we have here is very useful because in many situations this probability of A complement is more easily obtained by direct methods than going through the probability of A, and we are going to look at an example. Okay. So consider a system of 5 components being considered in series. These components are identical and they are being connected in series. Suppose that we denote a component that fails by F, that is failure, and one that doesn't fail by S, this for success. Let A be an event that the system fails. Okay, for event A to, it means that within this series at least one of these components should fail. If any of these components should fail, it means that the entire series is going to fail. So the outcome of A can include S, S, F, F, S, okay, which in this case means that the third component will be failing. Now also we could also have fail, fail, S, success, success, success. As long as there's there is one component failing, it means that this series has failed, which happens to be the event that we are looking for. Remember, A is an event that the system fails. So in case where we could even have SS throughout, but immediately one of these components fails, then it means that the event that we are looking for has been satisfied. And with this scenario, we can come up with about 31 different outcomes in which system or component within this series is going to fail. But however, let's look at an event A prime. That is if the event system should work. That is if all the components within the series all should work. And that will be only a single outcome, because that will be when all the series, all the components becomes are successful in the operation, that is SSS1 throughout. So if you like to estimate the probability of A, let's see how we are going to do this. Now remember that before we can achieve the probability of A, it means that we have to list all these 31 different outcomes. Remember, A is the situation or an event where the system fails. And this happens to be 31 different outcomes. However, if you look at the A complement, this A complement is only one outcome. Okay, and in chapter 4, in subsequent sections, we are going to see that if 90% of all components within a system or a sequence do not fail, then independently of one another, the probability of that event, that is the A prime with only one outcome, will be equal to 0.9 raised to the power 5, where this 5 refers to the number of components that we are looking at. So with this, all this gives us 0.59, and that happens to be the probability of A prime. So if you've been able to determine the probability of A prime, for us to get the probability of what? A, all that we have to do is just subtract it from 1. And that is just going to give us the probability of what? A. So other than going through trying to estimate all the outcomes of A, which is about 31, we could just go through by finding the probability of the A complement, which happens to be very easy. Then you just subtract it from 1, and that is going to give you the probability of A. As simple as that. So once we are able to determine this probability of 0.41, it implies that among the large number of such systems, roughly 41% is going to fail. So this is how the proposition 1 is being used for trying to estimate the probability of the complement instead of going through the whole thing. And this makes it a little bit easier to work with. So just as I said, when you are having difficulty calculating the probability of A directly, just think of trying to determine the probability of the A complement. Once you get this probability, you just subtract it from 1, and that gives you the probability of A. Now let's look at the second proposition. Now for any event A, the probability should be less than or equal to 1. Now remember that probability always ranges from 0 to positive 1. Okay, and for us to prove this, let's take a look at this. Now remember that probability of A plus probability of A prime should always give us 1. And remember that this is always greater than or equal to probability of A, because probability of A prime should be greater than or equal to 1. So if that happens, it means that if we should look at these two probabilities, if we should sum them, it should be greater than probability of A, because there's no way a probability in here could be negative. So it's either 0 or greater than 0. So if this happens to be greater than or equal to 0, then it means that their summation will definitely be greater than just the probability of A. So when event A and B are mutually exclusive, it means that probability of A union B is equal to that. Remember I told you from earlier sessions that when we should have a mutually exclusive event, we are just going to take off the negative probability of A intersection B. We are going to look at this very soon, into details very soon, and that is that. So let's see why we have to take away this probability minus probability of intersection of A and B. So for any event that are not mutually exclusive, it means that adding the probability of A and probability of B results in double counting, as I explained earlier. Okay, so that will brings us to the chapter proposition 3, that deals with addition of events that mutually exclusive. Now looking at this, we could see that for any two events, just as we did earlier, probability of A union probability of B, or probability of A union B, is the same as probability of A plus probability of B minus probability of A intersection 1B. Now note from earlier discussion that if you should have two events A and B and you should sum everything, you could see that this overlapping in here, there is going to be a double counting at this portion. So for us to do that, it implies that we have to take away this probability intersection of A intersection B. So this is just going to deal with or negate one part of this so that there's not going to be a double counting. Okay. So once we go through that, it means that we can determine the probability of A, that we have here, union the probability of B, so that we are going to leave out this portion so that we don't get to count this and this, making it a double count. So once we have a mutually exclusive event, it means that the probability of A union B is only going to give us the probability of A plus the probability of B minus all that we have in here. So to prove that, we go through this procedure and we get to that point. So once we are dealing with probability of A union B, this is decomposed into two disjoint events, that is A, that is as we have in here, and probability of event B intersection A prime. And remember that anything outside A refers to A prime. So event B intersection A prime is what we have in this section that we have here. So if we should add this A and that B intersection A prime, we get to have this addition. Now let's look at the B itself. B itself is also a union of two disjoint events, that is A intersection B and A prime intersection B. So for the B, there is just like the reverse of this, where in the first case we are going to keep all of the B, and the second case we are going to just take away this intersection part and only deal with this aspect of it. So that is this A intersection B is what we have here, and the next one is what we have also in there. So now let's look at this. If the probability of this B is equal to probability of A intersection B and the probability of A prime intersection B, then rearranging this, you could see that from the initial beginning, we remember that we said that probability of A union B is equal to the disjoint set of A and probability of B intersection A prime. So probability of A union B is equal to a probability of A and probability of B intersection A prime. Now remember that in this case too, we have probability of A prime intersection B. So with this, we could make this the subject from this equation. So once we make this the subject in this equation, we can replace it or we can substitute it into this term that we have here. And remember that A intersection B, A prime intersection B is exactly what we have here. But remember that these two terms are associative, commutative, so we can just interchange them. So once we replace everything that we have in here with this becomes probability of A as we had here. Then replacing all this, we have probability of B minus probability intersection B as we deduce from making this the subject of this equation. Now if we are to rearrange the terms, we could make this will be the same as P of A plus probability of B minus probability of A intersection B. And this is how we get to prove this addition law of two events. So just go through by splitting A union B into A and B intersection A prime, and this B part 2 also into these two components. Once we try to come back to our A union B and we split it into this side, all that we do, the making of this A prime intersection B the subject here will yield this, which when we substitute into this, we are getting this addition law right in here. So this is the addition law of probability, and let's see how this is being utilized in the field of what estimating probabilities. Now suppose that we have two mining companies. Let's take Goldfields and that of what Anglogold. Now for each of these mining companies, suppose that the events of Goldfields obtaining a certain profit is being denoted by G, and an event where Anglogold obtains certain profit is being denoted by event A. Now, G union A happens to be Goldfields profits and that of what? That of what? Anglogold's profit. So we could have a probability of G having to be 0.70 or 70, meaning that the probability of Goldfields obtaining a profit is 70%, and that of a probability of what Goldfields obtaining a profit is also at 0.4, that is about 48%. Now, in situations where they get to have or do some sort of collaboration, that is their intersection, that is intersection between Goldfields and that of what Anglogold, we could think of it as some collaboration or certain things that they do have in common, and that brings out about what 36%. Now, estimating the probability of Goldfields profit union that of what Anglogold's profit, this will be equal to probability of G plus probability of A minus probability of G intersection probability of A. Now remember that because they have something in common, that is why we have this negative sign here, and this is from the addition law of probability. Now probability of G has been given to be 0.7, that is what we have here. Probability of A has been given to be 0.48 as we have in here, and their intersection has been given to be 0.36. So once we simplify this, we are having probability of G union A to be equal to 0.82, and that will be their union or the profit for these two mining companies. Was trying to look at the two of them at a goal. Now let's also try to look at another instance where we like to look at our internet service providers. So in a certain residential suburb, 60% of all households get internet service from a local company. 80% get their television service from that same company, and 50% get both services from the company. Now, looking at this, if we were to estimate that one, for a select household that is being selected randomly, what is the probability that that household gets at least one of the two services from the company? And two, what is the probability that the selected household get exactly one of these services from the company? So let's try to find solution to the first one. That is the probability that, what is the probability that the selected household get at least one of these two stations from that company? Now, the term at least meaning that the person could either get an internet service or a television what service. So because of the term or, it means that we would have to find what the probability of internet service union the probability of what the television what service. So in this case, all that we are going to do is try to estimate probability of internet and probability of what the television what station, that is their union. So in this case, let's assume that we denote A to be an event where the household gets internet service, and B where the household gets TV service, and the probability that A intersection B, that is where both of the household gets both service. So from the question, we got to know that the probability of the households, about 60%, gets internet service from this company. So that is why we have probability of A equal to 0.6, referring to the 60%. Now in the case of the television station or the television service, 80% do get theirs from that same company. So probability of B, which happens to be household getting TV service, happens to be 80%. And remember from the last one, 50% get both services from the company. So that is why we have the probability of A intersection B giving us what? 0.5, referring to what? 50%. Now, going back to the first question, that what is the probability of getting that the selected household get at least one of these two services? Now, this English term at least means that the household could either get internet service or television what service. Now, because of the or, it means that we are dealing with what? The union. So it means that we have to estimate what the probability of A union B. And remember from the addition law of probability, once we are talking about union, that brings us to the addition law. So the probability of A plus the probability of B minus probability of A intersection B. And remember, we do have all our estimates in here. So probability of A equal to 0.6, probability of B equal to 0.8, minus their intersection, which was equal to 0.5, and that is just going to give us what? 0.9. So it means that the probability that a randomly selected household getting either at least one of these services will be equal to 90 or 0.9, which is the same as 90%. So it means that the household that we shall randomly select, 90% of them are likely to get at least one of these services. Now let's look at the second question, that what is the probability that the selected household will get exactly one of these services from the company. Now exactly one, meaning that it could either be the television service or that of the internet service only. Now the key word here is what? Only. So in this case, let's see how we are going to estimate this. Now if we were to represent our diagram or our question in a Venn diagram, this is how it's going to be. Remember that the intersection was equal to 0.5 and we had that of the internet service to be 0.6, that is the event, and this happens to be 0.8. Now remember that this 0.8 refers to everything of B, and 0.6 refers to everything of A. Now if we are to subtract our intersections from this, we are getting 0.1 and 0.3. So if we are to estimate the probability that a household gets only one of these services, it means that we have to calculate the probability of that. So in this case, this is how it is being done. Now looking at, we could just solve this right from the Venn diagram, but let's see how this is done. Because we are looking at only a service, we could either be only internet service or only TV service. We could just pick up this portion and add to this portion, so 0.1 and 0.3, which is just going to give us 0.4. Now that will be the probability of getting that, but let's see how we get to estimate this. So now you could see from the addition law of probability that probability of A union B is equal to probability of A plus probability of A intersection B. That is the B aspect of it. Now looking at this, we already estimated the probability of A union B. That was from the first question to be equal to 0.9. Now we are trying to look out for this term, which happens to be the probability of B only, which happens to be this portion that we have here. So in doing so, we already know our probability of A. So we know our probability of A union B to be 0.9, probability of A to be 0.6. So rearranging this, we get this whole term to be equal to 0.3, and that is just going to give us probability of B only. Now let's do the same for this section. And using the same formula, we already know our probability of A union B minus probability of what? B. We know this to be equal to 0.9 minus the probability of B, which is equal to 0.1. So this portion that we also have here, which is equal to what? The probability of what? A only, okay, gives us what? This 0.1, and that is why we have this portion. So for us to get the probability of only one service, it means that all that we have to do is just add this section and this section, and that is why we are getting what? 0.14. So the probability of exactly one, which is the same as only one, is equal to 0.4. That is to say that if we were to select a household randomly, then there is 40% chance that that household would only get exactly one service. So that is how this addition law of probability works. Now with this, let's try to dive more into this mutually exclusive events. And once we are saying that mutually exclusive, now if we should have two events and we term them to be mutually exclusive, it means that these two events has nothing or no element in common. So once it happens, so it means that this event will be standing on their own. There's not going to be any overlap, or there's not going to be any form of intersection. So once we have it in this case, and we like to estimate the union between these two events, then we are just going to have probability of A plus probability of B. And this time we are not going to include any minus probability of the intersection, because there's nothing common between these two events. So that is to say that the probability of A intersection B will be equal to 0 in this case, because they are mutually exclusive events. They have nothing in common, so they have no intersection. So that is how this is done. So if you should have an example with events that are mutually exclusive, it means that for you to get their union, just add the probability of A and the probability of the second event, and just add them without any intersection. And this is how the mutually exclusive event is being estimated. Now with these laws and this Venn diagrams we've been doing, we've been taking a look at two events. But what if there are three or more events? So let's look at the three events for now. Now, suppose that there happens to be three events, let's say A, B, and C. You could also determine their union, which is the same as their sum. So event A, event B, event C. Now for us to add them, this is the same as A union B union C, and this is equal to probability of A plus probability of B plus probability of C, okay, minus probability of A intersection B minus probability of A intersection C minus the probability of B intersection C, then plus A intersection B intersection C. Now let's see how we are explaining all this. Now just as we observed for the two events, anytime there's an overlap, it means that we are likely to count it multiple times once it comes to their intersection. So with this formula, we are going to add A, the event A, the event B, and then event C. Then subtract A intersection B. So we are going to subtract this portion. Then P intersection C, which is also this section, A intersection C, and also subtract B intersection C. That is what we have here. Then after, we are going to add P intersection B intersection C, which happens to be the middle portion that we have in here. So let me try to do this again so that I get to see this again if this will be possible. I think yeah. So that is that. So the first one is A, probability of A. So in doing so, let me take this color green. Oh no, 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 no. Can't I just, it's not working. So the probability of A is just as the one that we have here. Now probability of B will be equal to whatever we have in this section. And probability of C will be the one that we have here. So if we should subtract this intersection, subtract these two as well and subtract that, and at the end of the day you will see that all here will be what, blank. But if we add this portion to it, okay, we could get back whatever we missed, and that is this whole thing is going to fail. So that is why we get what, subtract A intersection D, A intersection C, and B intersection C. Then finally, after we are done with all of this, then we add everything what together. So that is what is happening in here. Now with this, let's see how we get to estimate probabilities was systematically. So consider a sample space that is either finite or infinite. When we talk about finite, it means that we have events within the sample space that has an n, a start to an end. But in cases where we have infinite, it means that we know the starting point, but we don't know where this is what ended. So that is also something. So for example, the testing of battery scenarios, we can have event 1, event 2 up to what, infinity. And that is an example of a countably infinite what event. Now, a sensible strategy for probability computation is to first determine each simple event probability with the requirement that all the summation of the probabilities should be equal to what, 1. Then the probability of any compound event A is computed by adding together all the probabilities for all the events that you have in A. So with this, we are going to sum all this that we have in A. So let's take an example of this to demonstrate this principle. And in doing so, we take a look at commuting a train from Takoradi to Takorwa, which they started not long ago. So with this question, I suppose that during off-peak hours, a commuter from Takoradi to Takorwa train has 5 cars. Now suppose that we have a train, forgive my train, and this train has 5 cars. So car 1, car 2, car 3, and car 4. They all have their, should I say, their wheels under them. So this happens to be my train, and it's commuting from Takoradi to Takorwa. Now, one thing that we observe, or if you happen to be a commuter who is conscious about your security, it's likely you are more likely to sit in the car 3 because of safety reasons. That is, if an accident should occur in front of this train, you are less likely to be affected if you are in this region. In that same case, if you are an accident, or if an accident should from behind the train, being in the middle, you are a little bit safer. So for any commuter who is security conscious, he or she is twice as likely to select this middle car than to select either the adjacent car, that is number 2 or number 3. So the probability for someone to sit in this middle car is twice as likely than to sit as what, this car 2 or car what, 4. So this car 3, car 4, and car 5, and 1 and what, 2. So this commuter who is conscious of his security is likely to twice as likely to sit in this car 3 than to sit in what any of what this adjacent what cars. Now also he is twice as likely to select the adjacent cars than to sit or select either car 1 or car 5. So it means that this commuter, if he doesn't get car 3 and the option available is either car 2 or car 4, he is twice as likely to sit in either car 2 or car 4 than to sit in either car 1 or car 5, because once it gets to that option, it means that you'll be some kind of one closer to the accident. That is if an accident should work. So the commuter is twice as likely to sit in the middle, that is car 3, than to sit at what the adjacent car, that is 2 or 4. But he is also twice as likely to sit in either car 2 or car 4 than to sit in car 1 or car 5. So suppose that we let P represent the car that is being selected. So we do have the probability of car 3, that is the commuter selecting car 3. And remember from the statement that he's twice as likely to select the middle car. So meaning the probability of what he's selecting car 3 is equal to what? Twice of what? Probability of he selecting what? Car 2 or car 3 or car 4. Remember that he is twice as likely, so 2 times of probability of car 2, and this also 2 times of what? Probability of what? Car 4. Now once it comes to the other side, remember we said that he is also twice as likely to select either car 2 or car 4 than to select either car 1 or car 2. So once it comes to car 2 this could be equal to what? The probability, or 2 times the probability of what? Car 1. So it's more or less like it will take twice the probability to sit in car 2 than in car 1. So the same thing happens here because of these extreme ends. So we have 2 times of probability of car 5, which is the same as what? P4. Now remember that this whole probability, if we should sum everything, all should give us what? 1, as we have here. Okay. So the summation of probability of all the events, which should give us 1, we can represent this as a linear combination of all the probabilities for each car. Remember for car 1, we have P1, and once we come to car 2, this is the same as what? Twice of what? P1, because we have P2 equal to what? Twice of what? P1. Then for car 3, remember that we have P2 to be equal to 2 times of what? P1, but P3 equal to twice of what? P2. And remember we have P2 to be equal to twice of what? P1. So if we like to estimate our P3, this will be equal to 2 times of what? P1 times what? 2. And that is also going to give us what? 4P1. So because remember that our P2 is equal to what? 2P1. And remember that our P3 equal to twice of what? P2. So we have what? 4 times of P1 for the third car, and we have 2 times of P1 for the fourth car, and finally we have P1 for the fifth car. Remember that car 1 and car 2, they had the same probabilities. So that is what we have in there. So if you would like to estimate the probability, it means that first of all, we would have to find the value of what? P1. And remember that the whole of these probabilities that we have here should give us what? 1. So in event, summing all this, which is going to give us 10P1, should be equal to what? 1. Okay? So making P1 the subject, it means that P1 will be equal to what? 0.1. So in this case, our P1, which is the same as our P5, remember that our P1, probability of car 1, probability of car 5 are the same. So it means that P1, probability of the commuter selecting car 1 and that of what? Car 5 is equal to what? 0.1. Meaning that there's 10% chance of the commuter selecting what? Car 1 or what? Car 5. Also, we could also look at probability of car 2 and that of what? Car 4. Once we have estimated this our P1, we could find our P2, which we have it to be 1, 2 times of P1, which is equal to 0.2. So meaning that the commuter, there is 20% chance that the commuter is going to select one P1, that is car 2, or the fourth what car. Now once it comes to the third car, that one is equal to 2 times of what P2. And remember we have P2 to equal 0.2, and that gives us what 0.4. So meaning that there's 40% chance that this commuter is going to select car 3. So with these properties, if any car is to be selected by this commuter, there's a high chance that is about 40% that this commuter is going to select what car 3. And that makes a lot of sense because we are all conscious once it comes to of these cars, and we always like or always prefer where it is safe. So this is a typical example of how we estimate probabilities systematically. So that is that. Now also the probability that one of the 3 middle cars is selected. So this is a compound event which is then equated to be, once we are dealing with probabilities, the probability that one of the 3 middle cars will be selected. In this case, we are dealing with only car 2, 3, and 4, and we know their value. That's 0.2, 0.2, and finally 0.4, and this is just going to give us what 0.8. So that is that. So now let's see equally likely outcomes, where we should have equally likely outcomes. That is throwing of a fair die or rolling of a fair coin, throwing of a coin or tossing of a coin, and rolling of a die, or selecting of one of the 52 cards from a deck of cards. Now we see that with all these repeatable experiments, because they all have equal chances of being selected, their probabilities distributed across all these outcomes, and that is being represented by this formula that we have here. So you count the number of observations all over the total sample space, and that is just going to give us that. So with this, let's take a look at this example before we bring this session to an end. Now suppose that for those of us who like to relax at the beach or something, it's quite interesting to take a book along so that you get to read this book. So suppose that there's an individual who would like to go relax at the beach, but as he or she is relaxing, he would like to take some books along so that he could read as well during the course of the relaxation. So suppose that you happen to be that individual and you have 6 unread mysteries, that is a form of books, and also 6 unread science fiction books. Now the first 3 of each type are hardcover and the last 3 are paperback. So for the 6 unread mystery books, the first 3 are hardcover and the last 3 are paperback. So we have 3 and 3. Now once it comes to the science fiction books, we also have 6. The first 3 are hardcover and the last 3 are also paperback. Now you have to consider an experiment such that we are going to randomly select one of the 6 mystery books and also randomly select one of the science fiction books to take on this relaxation treat at the beach. Let's say Busia Beach. Now if we are to number these books, that is number the mystery books, that is from 1 to 6, and number the fiction books to also 1 to 6, we can determine the outcomes of these books as we have in here. So in this case we could have 1-1, and that is book 1 from the mystery book and book 2 from the science book. So these are the various combinations that we could select to go to the beach with. So these are that. So in all this, you can see that we have about 36 outcomes. So let's take an event. Suppose that 9 of these outcomes are such that these books are paperbacks. Now let's take a look at this. We see that, remember that the first 3 books are hardcover and the last 3 are paperback. So all books, science fiction books, that is the 4th, 5th, and 6th, are all paperbacks. And for the mystery books, 4, 5, 6 are all paperbacks. So if you like to have an event where the randomly selected books are all paperbacks, okay, it means that the only situation where this is going to occur is when we have the last 3 books for each type of book being selected. So in this case, where we have the 4th book in mystery and the 4th book in the science fiction, remember the 4th book of mystery and the 4th book of science fiction are both paperbacks, because remember that we said that the last 3 books are all paperbacks. So this section that we have here will represent the section of books that are paperbacks for both mystery and that of science fiction books. So this is going to represent about 1, 2, 3, 4, 5, 6, 7, 8, 9. So among the outcomes that we have, 9 of them are going to be only paperbacks for both mystery and that of science fiction books. So suppose that also the probability that an event A, that the selected books are paperback, then it means that all that we are going to do is just count our outcomes that we are interested in the event. Remember that these outcomes is exactly 9, and remember there's a compound event, so 9 divided by the total sample, or the total number of outcomes that we have, which is equal to 36, and this gives us exactly 0.125. So in other situations where we could think of a situation where the books that are being selected will be only hardcover, it means that this is just going to be within this session, because remember the first 3 books are all hardcovers, okay, and this exactly is going to be 9 on 36. So with this, we can estimate our probabilities as we see fit. So this brings us to the end of this session, and with the next session we shall be looking at what we call permutations and combinations, which is a little bit interesting to estimate. So with that one, I'll see you guys there. So see you at the next lecture.